Okay. Now let me move on to entanglement-based QKD protocols. Entanglement-based QKD needs a special type of photon source that produces a stream of entangled photon pairs instead of a stream of individual photons. There are multiple different technologies that can be used to implement entangled photon pair sources. This illustration shows one particular implementation, which is called a Type II spontaneous parametric down conversion source, or an SPDC. The purple line is a pump laser that shines a stream of pumped photons into a particular type of crystal. That crystal causes some small fraction of the pumped photons to split into two separate photons called the idler photon and the signal photon. One of these photons is always horizontally polarized and the other one is always vertically polarized. All the horizontally polarized photons always exit somewhere on the orange cone, and all the vertically polarized photons always exit somewhere on the green cone. Now, we should look at the two lines where the two cones overlap. If a pair of photons exits on these two lines, they will be entangled with each other. You cannot predict which photon has which polarization, but when measured, they will always have the opposite polarizations, horizontal or vertical. Now, quantum entanglement is a difficult concept to fully grasp. In particular, we should be careful not to confuse it with just normal classical correlation. Let's consider the classical source that is shown in this diagram. When this classical source emits a photon pair, there's a 50% probability that the photon going left is horizontally polarized and the photon going right is vertically polarized. And there's also a 50% probability that it's the other way around. The photon going left vertically polarized and the photon going right horizontally polarized. The important thing is that as soon as the photon pair leaves the source, it's already one or the other. Now, of course, Alice and Bob don't yet know which it is until they actually measure the photon after it arrives. But that doesn't change the fact that it was already one or the other option as soon as the photon pair left the source and before Alice and Bob did the measurement. We say that the state is hidden until Alice and Bob do the measurement. Now, this is not entanglement. This is just classical correlation. What then is entanglement? Now, in this diagram, we have a source that does produce real entangled photon pairs. In the previous diagram, each photon was either horizontally polarized or vertically polarized as soon as it left the source. In this diagram, each photon is in some sense both horizontally polarized and at the same time also vertically polarized. It only becomes one or the other after someone, either Alice or Bob, does the first measurement. The terminology that you may have heard is that the state of the photons is described by a wave function, and the wave function collapses into a specific state when an observation is made. Now it gets even more bizarre. When Alice measures her photon, it causes the photon to randomly collapse in one or the other polarization. But it also causes the photon traveling to Bob to immediately collapse into the orthogonal polarization. This is bizarre because it happens instantaneously, which seems to imply that there's information traveling faster than light. All of this, to me at least, when I heard it the first time, sounds very metaphysical. It sounds like word games that could never be tested in experiments. Now, shockingly, in 1964, a physicist called John Stuart Bell devised an experiment that can in fact distinguish classical correlation from quantum entanglement. In other words, this experiment can determine whether quantum entanglement really exists or not. The original experiment was called a Bell test, but later a simplified version of this experiment was discovered, called the CHSH inequality after its four inventors. The experimental setup is very simple and shown here. We have a photon pair source, entangled photon pair source in the middle, and we want to determine whether the photons that it produces are really entangled or not. To find out, Alice and Bob each perform a series of Bell state measurements using a polarizing beam splitter and two single photon detectors. Alice and Bob also each have a polarization rotator, which allows them to independently choose their measurement basis. This is the same setup that we saw at Bob when we described the BB84 protocol. For each series of measurements, we keep track of the so-called coincident click counts. So for example, the number N10 that you see in the formula is the number of times that the 1 detector clicked at Alice at the same time as the 0 detector clicked at Bob. And then we take these N numbers and we plug them into this formula for E that is shown at the bottom of the slide. Now, in the previous slide, I mentioned polarization rotators, which allow Alice and Bob to independently choose their measurement basis. Alice randomly chooses her measurement basis for each arriving photon, either 25.5 degrees or minus 22.5 degrees. And Bob also randomly chooses his measurement basis for each arriving photon, but he picks between 0 and 45 degrees. Given that Alice and Bob randomly choose between 2 different measurement bases, we end up with 4 possible combinations, which are shown here. And then we can compute this E value that I introduced 2 slides ago separately for each combination of the bases. And then finally, we can plug those different 4 values for E in the formula for S shown on the right. Okay, the math really doesn't matter. What is important is what you can conclude from this S value. If the absolute value of S is 2 or less, it means that the photons were not entangled, but only classically correlated. If the absolute value of S is greater than 2, it proves that the photons were in fact quantum entangled. The higher the value of S above 2, the more entangled the photons are. And when S reaches the value of 2 times the square root of 2, the photons are maximally entangled. In 2022, these 3 gentlemen were actually awarded the Nobel Prize in Physics for doing this exact CHSH experiment and thereby proving that entanglement is real. There's one more concept that I need to introduce before I can get back to the QKD protocols, and that is the concept of monogamy of entanglement. Earlier, we saw that 2 photons are maximally entangled if the S value in the CHSH experiment is equal to 2 times the square root of 2. This is also referred to as maximal bipartite entanglement. The 4 Bell states, for example, the psi plus state, which is shown here, are examples of such states. The concept of monogamy of entanglement says, in essence, that if 2 photons are maximally entangled with each other, then it's impossible for a 3rd photon to participate in that to be entangled as well. And this turns out to be important for the security of entanglement-based QKD.